In this video, we will explain the Poisson distribution. A Poisson random variable describes the number of events that happen in a certain period of time. Here are some examples. Consider the number of customers visiting a library in a day, or consider the number of cars crossing a bridge in a day, or consider the number of gamma rays hitting a satellite in an hour. Now here's the definition of Poisson distribution. A random variable x has Poisson distribution with a parameter lambda. We write this as x is Poisson parenthesis lambda. The probability x equals k is defined as lambda to the k divided by k factorial times e to the negative lambda. Here k is equal to 0, 1, 2, and so on. First, let's verify that this probability here is indeed a probability mass function. So in other words, we want to show that the summation of these probabilities is 1. The summation k from 0 to infinity probability x equals k is equal to summation k from 0 to infinity lambda to the k k factorial times e to the negative lambda. This is equal to, now let's first move this e to the negative lambda outside of this summation. So this is equal to e to the negative lambda summation k from 0 to infinity lambda to the k factorial. And this summation is just Taylor's expansion for e to the lambda. So this is equal to e to the negative lambda times e to the lambda. This is 1. Next, we want to calculate the expected value of x. So expected value of x, this is equal to the summation k from 0 to infinity k times probability x equals k. And this is equal to summation k from 1 to infinity. Here we write the k from 1 to infinity because when k is equal to 0, this item is 0. So this summation can be written from 1 to infinity. So k times lambda to the k factorial times e to the negative lambda. So this k cancels the k in the factorial. So this is equal to summation k from 1 to infinity. The denominator is k minus 1 factorial. We're going to write the numerator as lambda times lambda to the k minus 1 times e to the negative lambda. So we can move the lambda here and e to the negative lambda outside of the summation. So this is equal to lambda times e to the negative lambda summation k equals 1 to infinity lambda to the k minus 1 divided by k minus 1 factorial. And this is equal to, now this is summation here is the expansion of e to the lambda, right? So this whole item is equal to lambda times e to the negative lambda times e to the lambda. So this is equal to lambda. Now we just proved that the expected value of x is equal to lambda. So next we want to calculate the variance of x. Now to calculate the variance of x, we need to calculate the expected value of ex squared. But instead of calculating ex squared directly, we can calculate this first, x times x minus 1. So we calculate the expected value for x times x minus 1. And we will show why this is more convenient. So this is equal to the summation k from 0 to infinity k times k minus 1 times probability x equals k. And this is equal to summation k equals 2 to infinity. Because when k is 0 and 1, this whole item is 0. So we only need to take the summation from 2. So this is equal to k times k minus 1 times lambda to the k divided by k factorial times e to the negative lambda. Now the k times k minus 1 cancels out k times k minus 1 in the denominator. So this is equal to k equals 2 to infinity. The denominator becomes k minus 1, k minus 2 factorial. Now we're going to write lambda to the k as lambda squared times lambda k minus 2 times e to the negative lambda. Okay, so now again, we're going to move this lambda square and e to the negative lambda outside of the summation. So this is equal to lambda squared times e to the negative lambda summation k from 2 to infinity lambda to the k minus 2 divided by k minus 2 factorial. Now this whole item here is the expansion of e to the lambda. So this is equal to lambda squared times e to the negative lambda times e to the lambda. This is equal to lambda squared. Now we just proved that the expected value of x times x minus 1 is equal to lambda squared. Now we can write this item as expected value of x squared subtract expected value of x. And we know, we just showed, this is equal to lambda squared here, right? So this is equal to lambda squared. So this implies expected value of x squared is equal to expected value of x plus lambda squared. This is equal to, now we proved that expected value of x is lambda, so this is equal to lambda plus lambda squared. Now, so this proved that the expected value of x squared is equal to lambda plus lambda squared. Now the variance of x is equal to expected value of x squared subtract expected value of x squared. So this is equal to, because expected value of x squared is equal to lambda plus lambda squared, and expected value of x is lambda, so subtract lambda squared. So this is equal to lambda. So there you have it. So we proved that expected value of x is lambda. The variance of x is also lambda. So this is the interesting property of the Poisson distribution. This is actually very useful because this gives us an interpretation of lambda. So lambda is essentially the expected value of x. Remember, x usually describes the number of events given a certain period of time. So this, we can use this, the expected value of x to interpret the value of lambda. Now let's look at an example. Now let's look at the following example. And suppose a factory makes electric devices. On average, it produces 5 defective devices in a day. Now the first question is, let's define a random variable to describe the number of defective devices in a day. The second question, what is the probability to have less than 3 defective products in a day? Now let's look at the first one. Now, as we described in the previous page, we can use a Poisson distribution. So suppose x is equal to the number of defective. Now, if x is the number of defective devices, we can model x as a Poisson distribution with the parameter lambda. So we show in the previous page that lambda can be interpreted as the expected value of x, or the expected number of defective devices in a day. And the question tells us, in the question we know that there are 5 defective devices in a day on average, so which means lambda is equal to 5. Now the second question is the probability to have less than 3 defective devices. So we want to calculate the probability x is less than 3. So if x is less than 3, x has 3 possible values. So x could be 0, s could be 1, and x could be 2. Okay, so this is equal to, now we can use the Poisson distribution formula to calculate these items. So the first one is lambda to the 0 divided by 0 factorial e to the negative lambda. The second one, lambda to the first divided by 1 factorial e to the negative lambda, plus lambda to the second divided by 2 factorial times e to the negative lambda. So this is roughly 12.5%. Thank you for watching.